It is my great pleasure to welcome you to the world of learning new concepts and current trends, so let's start. A single corrupted data entry in a system doesn't sit in isolation, it propagates. If an application pulls a malformed ID number, or a text string where it expects a price, the mathematical logic breaks down, and the failure ripples outward. In a live environment, a simple typo or a duplicated row can cause inventory systems to crash during a checkout process. This directly results in lost revenue and broken user experiences. To prevent this, architects rely on a concept called database integrity. This is the overarching framework that guarantees the data stored in a system is strictly correct and logically consistent at all times. Because human users will always make mistakes, developers cannot expect perfect data entry. Instead, they build automated, physical rules directly into the database architecture. We call these rules constraints. This diagram shows the three primary types of constraints used in database management systems. Working from the smallest piece of data up to the full network, these are domain constraints, entity constraints, and referential constraints. Database integrity actively filters incoming information. It physically blocks human error from ever entering the system in the first place. Let's look at the absolute smallest unit of a database, a single data cell. Imagine a user is filling out an employee profile and accidentally types their phone number or a string of letters into a column explicitly designed to store numerical salary data. This is where domain integrity comes in. It is the rule that forces the values inside a column to adhere to strict criteria, like a specific data type, a required format, or a defined numerical range. This table illustrates a domain integrity violation. In the bottom row, the salary value 697ABC includes letters. Because the column domain is defined strictly for integers, the database flags this as an error and rejects the input. Applying these rules is required for the first step of database normalization. To achieve first normal form, or 1NF, every value in every cell must be atomic, meaning it holds only one individual piece of data, and it must be strictly valid according to its column's rules. If the raw ingredients inside these individual cells are invalid, the structural reliability of the entire database is compromised from the ground up. The perspective now expands outward from that single cell to encompass an entire horizontal row, which represents one complete user record. If a system contains two completely identical rows of data, the computer has no mathematical way to distinguish between them when it needs to update or delete a specific record. To solve this, we use entity integrity. This rule dictates that every single record must be assigned a unique identifier, known as a primary key. Looking at this entity integrity diagram, the ID cell is blank. Primary keys must be unique and never empty, known as null. In MySQL Workbench, developers enforce this by checking the PK box for primary key and NN ensuring not null. Establishing these unique keys allows a table to reach second normal form, or 2NF. In this state, every piece of non-key data, like a customer's name or age, depends entirely on that unique primary key to give it context. Without entity integrity, a database suffers from identity collapse. It becomes entirely unable to reliably locate, update, or remove specific information. When we zoom out one final time, we see that this single table operates within a larger system, floating alongside several other distinct tables. These separated tables need a way to communicate. They do this utilizing a foreign key, a column in one table that acts as a direct bridge to a primary key in another table. If a purchase order points to a customer ID that was deleted, you get an orphan record. The data points to a target that simply does not exist. We prevent orphan records using referential integrity. This rule dictates that a foreign key must perfectly match an existing primary key in the target table, or it must remain entirely blank. This interface panel illustrates how developers construct these secure bridges. The foreign key labeled Artist ID is explicitly mapped to the Artist ID column in the referenced music.artists parent table. Applying these strict relationships helps a database achieve third normal form, or 3NF. This process removes transitive dependencies, which occur when non-key attributes depend on other non-key attributes, so that tables connect cleanly and logically. Referential integrity acts as the gravitational pull of a database. It prevents dead ends and ensures all the relational logic holds together under pressure. We now have a fully resolved ecosystem. The data is clean at the cell level, unique at the row level, and perfectly linked across the entire network. Constraints are often viewed by end users as frustrating error messages that interrupt typing. In reality, they are the load-bearing walls of computer science. By systematically applying domain, entity, and referential constraints during the normalization process, developers transform chaotic data into a strict single source of truth. Open your database management software and manually configure these 3 constraints. Use the table editor to set your data types and primary keys, and the relationship editor to map your foreign keys. Establishing these structural rules is a requirement before we can move on to exploring advanced database design principles in the next session. Mastering database integrity is the definitive threshold you must cross to evolve from a spreadsheet user into a true database architect.